Voyager 1 has left the bubble around the sun and entered interstellar space, the space between stars.
It's amazing that Voyager has operated 36 years. Launched in 1977, traveled past the gas giant planets, and now off into interstellar space. A radio telescope took a radio image of Voyager 1 spacecraft slightly over 11 billion miles from the Earth. And it's a very small radio dot amongst a sea of darkness.
We have an instrument on Voyager which can measure the density of the ions, the plasma which is out there. In March of 2012, it turns out there was a massive eruption from the sun which eventually reached Voyager 1 in April of 2013. When that blast wave reached Voyager, it caused the plasma around Voyager to vibrate or oscillate in a certain particular tone. Literally, they're the sounds of interstellar space. And by measuring that sound wave, we could measure the density of the plasma, and we're amazed to find out that we were in interstellar space. This is a historic milestone in the great journeys of exploration that have been undertaken by humankind. Well, it is quite remarkable when you think about it, that far off now at ever increasing distances, there's this little vehicle, two of them, which were built here many years ago and launched 36 years ago, now on a journey that will basically last for billions of years.
We don't really know on Earth why you get thunderstorms at the rate we get them. We look at Saturn, they're very infrequent.
We were pretty sure that lightning exists there, but we actually couldn't see it. It's a giant planet with huge atmosphere, and there should be a lot of weather there.
We had heard the lightning on the radio instrument on Cassini, but you hear static on the radio signal, but you can't pinpoint where it's coming from. We had to use a synthetic noise because the actual noise that the radio instrument is picking up is beyond the human ear. So we picked a noise that sounded like an electrical discharge. In other words, a big spark. That's what lightning is. It's taken us a long time to see the lightning, and that's because normally the night side of Saturn is very bright because the rings are shining down all the time. The night side of Saturn is brighter than Earth under a full moon.
The strategy we chose was to look at the equinox. And the equinox is when the sun is in the ring plane, so it doesn't illuminate the rings that much. And rings become dark, and this night becomes dark.
When it finally got dark enough at night, we pointed the cameras there, and wonder of wonders, there were lightning flashes, and took a series of pictures. And in one picture there'd be no lightning flash, and the next picture there'd be a lightning flash. And at the same time, you hear the noise over the radio instrument.
And we actually saw it. I didn't believe it.
The lightning storms on Saturn are very much like lightning on Earth. You get the same strength lightning storms, or thunderstorms. They have the same strength, but they're just much less frequent. I'm enjoying the show. You can see the aurora in certain wavelengths, even from Earth. Hubble sees the ultraviolet aurora. what's new is that we're up close with Cassini, and that enables us to see details that we've never seen before. Cassini cameras are using visible light, so this is the first time we've got really nice images in visible light. I saw those auroras shimmering and changing with time, sort of flickering, and I just liked the action. I thought it was beautiful. We're always looking for similarities between planets, especially things that we can compare with Earth. In fact, the auroras on Saturn have a lot of similarities to the auroras on Earth. Both on Earth and on Saturn, you have charged particles from outer space crashing into the upper atmosphere and causing it to glow. The magnetic field guides the particles into the high latitudes. So there's northern lights and southern lights, and they're both near the poles on Earth, and that's also true on Saturn. It's near the poles that the magnetic field guides the particles into the atmosphere. I'm a weatherman. I like weather at all altitudes, from hurricanes near the ground to the weather of the top of the atmosphere. The vacuum of space has weather, changing conditions. We're learning about space weather.
The MMS mission is a mission consisting of 4 spacecraft which will fly in close constellation to measure a process called magnetic reconnection.
The universe is full of plasma and it's full of magnetic fields, and all over the place in the universe you have one plasma colliding with another. An example of that is the solar wind coming in and colliding with Earth's magnetosphere. And then the magnetic energy in the plasma, some fraction of that magnetic energy is converted very rapidly into plasma energy. So you can think of it as kind of like a magnetic explosion. And the reason this is important is because these explosions drive a lot of the weather patterns that we see in the magnetosphere, and so what space scientists like to refer to as space weather. And these space weather phenomena can have impact on our everyday lives. It can actually affect communication satellites, the power grid. So we'd really like to understand how these magnetic explosions work.
We need to measure reconnection in more than one location. We need to measure it in basically how it varies in space, how it varies in all 3 spatial dimensions. And that requires a tetrahedron. The additional fantastic benefit that provides is that it will actually enable us to recognize that we are looking with a reconnecting region much easier than a single spacecraft.
The ideal situation is that we would like the 4 spacecraft to kind of be surrounding this region where the explosion is happening. So the separation of the spacecraft is about 10 to 100 kilometers, which may seem like a long distance. But in terms of the magnetosphere, which is absolutely huge, this is really a microscopic region that we're trying to cover.
MMS has, in a nutshell, 2 orbital phases which are designed to study reconnection.
On the day side, basically you have a situation where the solar wind is just constantly running into Earth's magnetic field. And this is really great for MMS because we know that at some point MMS is going to encounter this region, and our hope is that since this process is always happening, we're going to get lucky and actually fly right through the magnetic explosion as it's happening. Now on the night side, the situation is a little bit different. So what happens is you have a more gradual buildup of magnetic energy in the tail, and these reconnection processes, these magnetic explosions, can just sort of pop off randomly. We don't really know when it's going to happen or where it's going to happen in the tail.
We need to understand both of those if we want to understand how the magnetosphere works, and we believe that both of those scenarios are also very important for other applications, such as on the Sun, in the solar wind, in planetary magnetospheres, and in many astrophysical objects, as well as in the laboratory.
We hope that it's going to allow us to improve our models so that we can put the right physics in it and actually make predictions about where and when reconnection is going to happen, and this will help us make our space weather models more predictively powerful. The instruments that are actually going to be measuring the particles in space are collecting them much more rapidly at a much higher cadence than they have on previous missions, about a factor of 100. So whereas it would take a previous generation particle instrument about 3 or 4 seconds to build up the whole picture of the sky, it's going to take MMS about 30 milliseconds. So it really is sort of game-changing technology.
Deep within their roiling clouds, thunderstorms hold an elusive surprise. Under just the right conditions, they produce some of the highest energy radiation naturally found on Earth, terrestrial gamma ray flashes, or TGFs for short. Studies by NASA's Fermi Gamma Ray Space Telescope have shown that TGFs fire up about 1,100 times a day. Now, new research combines Fermi detections with ground-based radar and lightning location data. These studies show that TGFs come from more diverse types of storms than previously thought. In a thunderstorm, collisions among rain and snow cause different parts of the cloud to develop positive and negative electrical charges. When the strength of the electric field overcomes the insulating properties of air in the thundercloud, a lightning flash occurs. Most lightning occurs entirely within the cloud and is called an intra-cloud flash. All lightning produces a strong and sudden change in the storm's electric field, but the upward portion of an intra-cloud flash sometimes sends a surge of electrons rushing toward the upper part of the storm. Reaching speeds nearly as fast as light, these accelerated electrons give off gamma rays when their paths are deflected by air molecules. Using global lightning location networks, scientists can determine a TGF position more accurately than with Fermi data alone. 24 localized TGFs occurred within areas covered by next-generation weather radar systems. This gives scientists the opportunity to begin studying the kinds of storms that produce TGFs. These slices of radar data capture different types of storms encompassing a wide range of updraft strengths. Even the weakest of them produced a TGF. Another finding, TGFs seem to occur in the same altitude range, between 7 and 9 miles high. Lightning can form at much lower altitudes, so there's every reason to think TGFs can too. But gamma rays from TGFs occurring deeper in the atmosphere are greatly weakened. They're too dim for Fermi to detect, which probably means the satellite is undercounting them. TGFs may be far more common than we think. With this knowledge, scientists can design experiments to track storms and study how TGFs relate to their strength and evolution. This will give us an even better understanding of planet Earth's most powerful natural particle accelerator.
All of these spectacular happenings are visible manifestations of its existence. An electrical circuit that links the top of Earth's atmosphere, where charged particles are plentiful, to the Earth hundreds of miles below. Scientists at the University of Colorado, Penn State, and the National Center for Atmospheric Research are working to develop a scientific model of the processes across various spatial and time scales within the global circuit.
So one of the important aspects of this project is that there have been measurements taken about the electrical system for the last, 90 years, since 1930, for nearly a century. But there are no really good established models that allow one to verify the interpretation of those measurements and the physical pathways that lead to those measurements. Some of them have profound implications, but we need models to establish their credibility.
Sprites, elves, and blue jets, all shown on this mural, are collectively called transient luminous events, or TLEs, and are believed to be part of the global electric circuit. Red sprites, first verified in 1989, occur from cloud tops up to 95 kilometers, or approximately 10 to 60 miles, in the atmosphere directly above lightning strike activity occurring below. They last no more than a few milliseconds and can resemble carrot tops, columns, or jellyfish in shape. Elves are large, expanding, donut-shaped luminous events, up to 190 miles or 300 kilometers across, that occur for only 1,000th of a second. They too occur over lightning activity, but are believed to result when an energetic electromagnetic pulse propagates from lightning into an area of the atmosphere called the ionosphere. It's brimming with electrically charged particles and at times auroras. It extends from about 35 to more than 1,000 miles in the upper atmosphere. Lastly, blue jets emerge from the top of thunderclouds, then fan out and disappear after about 1/10 of a second, at heights of approximately 40 to 50 kilometers or 20 to 30 miles. They are the only transient luminous event not directly associated with cloud-to-ground lightning. They were first documented in 1994. We have a lot more to learn about transient luminous events and their role in the global electric circuit. For that matter, we have a lot more to learn about the circuit's many contributors, from clouds to atmospheric particles and more. Scientists working at the frontiers of this science are leading the way.
We think that by pursuing an improved knowledge of the whole global electric system, that discoveries will emerge that we might not have even have anticipated. And that's the way basic research goes. It wouldn't be called basic research if we already knew what the outcome was going to be.
What is the cumulative effect of Earth's thunderstorms that charge the planet's electric circuit up through the ionosphere? What processes contribute to earthward current on clear weather days? What unknown roles might electricity play in our weather, our climate, and throughout our amazing, electrified atmosphere.